In this video, we're going to cover section 5.2, which is properties of rational functions. So if you remember, we said in the prior video that chapter 5, we're going to discuss specifically polynomial functions, which we did in 5.1, and rational functions, which we're going to actually do in two sections, 5.2 and 5.3. So the section in polynomials 5.1 was really long. It was jam-packed with information, and if we tried to take all the information for rational functions and put it all in one section, it would be even more jam-packed than 5.1. So this author breaks it into two pieces. I really like that he does this. So let's take a look at what we're going to do in 5.2. So the first thing we're going to talk about here is just the general form of a rational function, and basically all we're talking about here is a fraction. All right, so the numerator of the fraction is a polynomial on its own. The denominator is a polynomial on its own, and together the division of those two polynomials creates what we call a rational function. And then just a reminder that we can't have division by zero. So whenever we look at these rational functions, we're going to be concerned about where we would have division by zero. That'll be a part of our conversation. So speaking of that idea of division by zero, let's look at a couple examples. We're going to find the domain of a rational function. This is our first objective or first skill for this section. So letter A gives us the rational function 2x squared minus 4 over x plus 5. So when we talk about the domain of that rational function, right, we can't have division by zero. So we're going to say x plus 5 can't equal 0, right? Or in other words, x can't equal negative 5. So the domain is going to be all real numbers except x equal negative 5. And the simplest way for us to write that would be in the set builder notation, where we say it's the set, right? So we use the curly brackets to denote set of all real numbers x, and then this line means such that x cannot equal negative 5. So any real number that's not negative 5 is in the domain. Let's take a look at a second example. So in this example, we look at the rational function 1 over x squared minus 4. Now, if we were to do the work here, right, what I would do is I would say basically, where does x squared minus 4 equal 0? And if I use factoring, right, let me write a little bit here. If I think about factoring, I could say x minus 2 times x plus 2, and I set each of those factors equal to 0. So kind of like we talked about in the prior section for polynomials, I'm finding the zeros of the denominator. So whatever values make the denominator 0, those are going to be excluded out of the set of real numbers. And so again, in set builder notation, we would say it's the set of all real numbers x, such that x cannot equal negative 2, comma, x cannot equal positive 2. All right? So any real number except 2 and negative 2 are valid for the domain of this rational function. All right, so let's take a look at a third example. So third example, here's another rational function. And if I were to set the denominator equal to 0, what we're going to notice is there's never any real valued number where the denominator equals 0. All right, so for example, if I were to take x squared plus 1, and I were to set it equal to 0, and I'm saying question mark, where does that occur? So I'll subtract the 1 to the other side, so I get x squared equals negative 1. And then obviously I'm going to square root both sides of the equation here. So I'm going to have plus or minus the square root of negative 1. And so remember that the square root of a negative is an imaginary number or a complex number. So what that means is there's no real valued number for which I would have division by 0. So in this particular case, I would never have division by 0 for any real valued x. So we're going to say the domain is the set of all real numbers. All right, so for our next example, we're going to look at negative x squared plus 2 all divided by 3. And again, in this example, the domain is the set of all real numbers. Because when I take negative 3 and set it equal to 0, negative 3 will never equal 0, no matter what value of x I pick. So in this case, this rational function is the domain of all real numbers. All right, our next example, we're going to look at x squared minus 1 divided by x minus 1. All right. So in this example, we notice that we have x minus 1 equal to 0 gives me x equals 1. So x cannot equal 1 for this function, and in set builder notation, here is our domain. All right, now one thing kind of important to notice here, and some of you might have caught this, maybe you haven't, no big deal, but notice that the numerator would factor as x minus 1 times x plus 1, and the x minus 1 factor would cancel with the denominator. Right? So it's important for us to notice, right, that x minus 1, the numerator factors, and the x minus 1s would in essence cancel each other out. And so this rational function, if I were to simplify it, would turn out to be the line x plus 1. Right? And in fact, if I graph this rational equation, it's going to look just like this line, right? However, even though I can do that cleanup, that simplification, the rational function as it is given does not have x equals 1 in the domain. And we always just want to be a little careful here when we're asked questions of domain. It is important for us to simplify expressions. However, the function is what the function is, and we're going to always exclude 1 out of the domain of this function. Right? So notice, right, we're saying that this function and this function are equal to each other everywhere except at x equals 1. And let me show you what I mean by that. Okay, so I brought up my graphing calculator here, and I want to point out to you that in y1 I have typed this rational function, x squared minus 1 over x minus 1. And I just want to point out to you here something that's really, really important when you're graphing rational functions is we always put parentheses around the numerator and then parentheses around the denominator. That's really important. Right? So I'm going to use these left and right parenthesis buttons here. So I'm parenthesize the numerator and parenthesize the denominator. So here's r of x, our rational function, and then we said through simplification that it is the same thing as x plus 1. So in y2 I graphed x plus 1. Right? Now, we talked about this in a prior video, and what I'm going to do is I'm going to move over here to the left, and I'm going to hit enter a couple times, and I'm going to change it to that line with a circle, right, so that when it graphs, it will graph with a circle. Right? So when I hit graph, we're going to see the rational function graph first. There's y1, the rational function, and then here comes y2, the line, x plus 1. So we can see that these two graphs lie right on top of each other. They really are the same function. However, at x equals negative 1, they are not the same. Now from the graph, we can't really see that. So what I'm going to do is I'm going to go to the table. So I'm going to do second graph and go to the table. We're going to notice that at all values of x, let me scroll up, all values of x, these two equations are equivalent. Right? So the rational function right here in y1 and the line right here in y2 are the same. Right? And I notice I said something wrong a second ago. I said at x equals negative 1 they weren't the same. Right? That's not true. At x equals positive 1 they won't be equal, and we can see that right here. At x equals positive 1 the rational function has division by 0, so the calculator gives me an error, and the line gets a value. So these two equations are identical except where we have the division by 0. And again, from the graph it's hard to see that, right? But those are definitely the same. Okay, so anyway, just pointing out to you that when we have a rational function, we usually want to simplify it, but when we're asking the question of domain, we don't simplify. We look just as the function is given from that point. All right, so just to further illustrate this to you, I brought up Desmos and I typed in my rational function x squared minus 1 over x minus 1. I just wanted to show you, like we've talked about before, if I just kind of hover my mouse and I click and hold, I can trace. So I'm holding the mouse button and I'm tracing, right? And it's plotting all of these points. I just want to show you, this is pretty cool. Right when I get to x equals 1, it's going to say it's undefined, and in fact that point will turn into an open hole. Let me see if I can get this to work. Oop, check it out. So notice the point on the graph is now an open hole, right? It can't plot a y value. That's pretty cool, and it tells me the y value is undefined. Now if I move off of that, it starts to plot y values, and it encloses the point because it's plotting y values, right? And when I get to x equals 1, it's going to leave me an open hole because that is an undefined point. All right? So pretty cool that Desmos will actually do that for me. My graphing calculator doesn't really do that for me, but Desmos will. It's just kind of a neat little feature there. Okay, so one other thing I want to explore here real quick with you graphically. This example that we just graphed with letter E is a very unique type of graph, right? I mean, the fact that this rational function looks like a line, that's not pretty typical. What's pretty typical is something like we might see in letter B. So when we actually get division by zeros, what does that mean graphically? All right, so what I did was in Desmos, I typed the equation 1 over x squared minus 4. I just want to point out to you what's happening here, right? At x equals 2, where I have division by 0, I get this really interesting behavior where the graph is kind of like broken, right? And out here at x equals negative 2, I get this interesting behavior where the graph is kind of broken there. And what we're going to do in just a second, we're going to officially call that a vertical asymptote. So what's happening is the graph is trying to like bend around the division by 0. So as I plot x values that get close to 2, the graph just kind of explodes in value. It doesn't want to allow me to plot x equals 2, right? So it just kind of goes down to negative infinity. And when I approach 2 from the right, again, the graph is kind of bending around x equals 2, and it's never going to actually allow me to plot x equals 2 because that's an undefined value. And this is what we call an asymptote, right? And the same thing on this side at negative 2. As I get closer to negative 2 for x values, the y values just get bigger and bigger and bigger. And the graph's kind of bending around the division by 0. So that's what we call asymptotic behavior. And this is pretty typical of what a rational function looks like. All right, and something else that's really interesting to notice is not only does this graph have like asymptotes in the vertical direction, it also has asymptotes in the horizontal direction. Notice that as I let x get more and more negative, the y values get really close to 0, but they don't ever seem to touch 0, right? And ditto in this direction, as I go out towards positive infinity on the x-axis, the y's just get smaller and smaller and smaller. Right, let me zoom out a little bit, right? So it doesn't matter how far out I go here. Look, the y's are just getting smaller and smaller and smaller. All right? So there's a horizontal asymptote on this graph, and there's a vertical asymptote on this graph. So let's explore an example where we see vertical and horizontal asymptotes, but let's pick a little bit easier of an example to look at. So let's take a look at the graph of y equals 1 over x. All right? Now, first of all, let's take a look at like as x gets really big. Okay, let's look at the horizontal asymptote. So if I'm just going to plot some points, right? Let's for this particular example, let's say I plot x equals 1. I get y equals 1 over 1, which is 1. If I pick x equals 10, I get 1 over 10, which is 0.1. Right? So there's that y value. If I pick x equals 100, I go really far out to the right of the graph. I get 1 over 100, which has a decimal 0.01. Pick x equals 1,000, I get 0.001. And then ditto if I go way out on the left of the x-axis, right? So if I pick x equals negative 1, I'm going to get 1 over negative 1, which is negative 1. If I pick x equals negative 10, I'm going to get negative 0.1, negative 0.01, negative 0.001. So if I were to plot those points, right, as x gets really big to the right and really small to the left, right, I'm going to see something kind of like this. The y values get closer and closer to the x-axis, but never really touch it. That's the horizontal asymptote behavior that we're getting. And that's what we saw on that graph on Desmos just a second ago. Now let's look at what happens when we get really close to the division by 0. Kind of like we saw on that graph on Desmos, we're going to get the vertical asymptote. So let me pick values of x that get really close to 0, where my division by 0 is, right? So I'm going to pick values of x that come from the left and get really close to division by 0. Then I'm going to pick values of x that come from the right and get really close to division by 0. So let's take a look at a table. Let's plot some points, right? So if I come from the right first, let's suppose I pick x equals 1, x equals 0.5, x equals 0.1, 0.01, 0.001. So if I pick x equals 1, right, again, I'm going to get a y of 1. If I pick x equals 0.5, 1 over 1/2 is 2. If I pick x equals 0.1, 1 over 1/10 is 10. 1 over 100th is 100. 1 over 1,000th is 1,000. And so what's going to happen is as I get closer to my division by 0, my y values are getting really big. And the same thing's going to happen in the negative direction. So if I plot those values, my graph is bending around the division by 0, and I'm getting that vertical asymptote. Right now, what we don't really want to do in this class is have to plot points every time to sketch the graph. So similar to what we talked about with polynomial functions, we want to develop our tools of analysis. We want to be able to look at the equation and figure out the behaviors, right? Analyze the behaviors of the function. So we don't really want to lean on plotting points. But what I like about plotting points in this case is it kind of illustrates for you where these behaviors come from. So basically what we're going to notice, and we'll summarize this in a second, at division by 0, I'm going to tend to find my vertical asymptotes. And then when I look out at the ends of the graph, I'm going to tend to find my horizontal asymptotes. All right, so let's talk about those a little bit more specifically. All right, so the book defines formally what a horizontal asymptote. And it basically says as x goes towards negative infinity, or as x goes towards positive infinity. So we're looking out at the far ends of the graph. We're looking out far to the left of the graph. We're looking out far to the right of the graph. And if the y values approach a fixed number, we're going to call that the horizontal asymptote. So a couple examples of what that might look like, right? So as x goes out towards infinity, notice the y values of the graph approach that horizontal line. We're going to call that my horizontal asymptote, right? Or in the other direction, as x goes to negative infinity, the y values are approaching some horizontal line. We would call that the horizontal asymptote. So this is the formal definition of a horizontal asymptote. In just a second, we're going to talk about how to find those behaviors for a specific equation. So then the vertical asymptote, right? So the formal definition of a vertical asymptote basically says as we approach some number, right, that's typically going to be the division by 0 value, but as x approaches some fixed value, if the y values shoot off to infinity, then that x value is our vertical asymptote. And the graph of R will never intersect that vertical asymptote because it is a division by 0, right? So visually speaking, right, as we approach C from the right or we approach C from the left, my graph is shooting off to infinity, right? Or I could have the graph bend in different directions. So as I approach from the right, the values shoot off to positive infinity. As I approach the value of x equals C from the left, the graph shoots down to minus infinity. So this is the formal mathematical definition. Right? I know sometimes these definitions sound a little confusing, so let's look at some specific examples. All right, so the theorem in the textbook basically says what we've already seen visually, which is that the vertical asymptotes are going to occur when there's a 0 in the denominator. So the division by 0 is going to typically produce the vertical asymptote. Now there's one kind of exception to that rule, and we'll see that in just a second. So here's a first example. Consider this rational function 5x squared over 3 plus x. Right? So if we're going to look for the vertical asymptote of this function, we're going to set the denominator equal to 0. And that's going to produce the vertical asymptote of x equals negative 3. All right, so I brought up Desmos real quick, and I graphed that rational function 5x squared over 3 plus x, and I also graphed the vertical line x equals negative 3. And I can see the asymptotic behavior to the line x equals negative 3. So the graph, right, this rational function has a vertical asymptote at x equals negative 3, and I just wanted to show that to you visually there. So x equals negative 3, the division by 0 is the vertical asymptote for this function. So let's take a look at another example. So let's suppose we have the function x minus 3 all over x plus 2 times x minus 2. And again, if I'm looking for division by 0 here, I'm going to set x plus 2 equal to 0, and that's going to give me x equals negative 2. And I'm going to set x minus 2 equal to 0, and that's going to give me x equals positive 2. So I'm going to find the zeros of the denominator, and those are going to be my vertical asymptotes. All right, so again, I brought up Desmos really quick, and I graphed our rational function for that example. And then I graphed the two vertical asymptotes, right? And we can see definitely at 2, there's vertical asymptote behavior to my graph, right? And at x equals negative 2, there's vertical asymptote behavior there as well. All right, now if I bring up my graphing calculator real quick, I just want to point out to you that, right, here's my rational function over here. And in my graphing calculator, I have to put parentheses around the whole numerator. And then I'm going to put an extra set of parentheses at the beginning and the end of my denominator to tell my calculator that all of that stuff, the x minus 2 times x plus 2, all of that's in the denominator. All right, now I have an older version of the TI-83 as an emulator here, but I just want to show you what happens on my calculator. That if I do a standard zoom, let me do a zoom standard, it looks really funny on my calculator. So my calculator is doing the best that it can to plot points and connect the dots, and it struggles. right? So we can see that what the calculator tries to do is it plots a point down here, and then it plots a point up here, and it tries to connect them with a line. Now remember that vertical line is not actually a part of the graph, right? Kind of like we can see on Desmos here, right? If I delete these two, right, that vertical line is not a part of the graph. Those are asymptotes. I can't plot points when x is 2 or negative 2. So the calculator is doing the best it can, and it's connecting those points incorrectly. And then look at what it's doing here. I mean, it's really struggling drawing this asymptotic behavior here. Now on my calculator, if I do a zoom decimal, I do zoom 4, it does a little better of a job, so it doesn't connect the points. I mean, even still, it struggles right here. I mean, this graph should extend forever and ever and ever down to negative infinity, and the calculator's struggling with that. So just keep your, keep it in their mind that when you use technology like a TI, it's doing the best that it can to plot points and sketch the graph. All right, Desmos is just a little bit better at handling it. But calculator, the newer version of the calculator, TI-84s that are out there, do a little bit better job than mine, but sometimes they will struggle. All right, let's just come back and take a look at our next example. So our next example, we're looking at x minus 1 over x squared plus 5x plus 4. So to find the vertical asymptotes here again, remember we're going to take the denominator, we're going to set it equal to 0. So we're finding the zeros of that quadratic function. Right? So I'm going to take that quadratic, I'm going to factor it, set it to 0. I'm going to get x equals negative 4 and x equals negative 1. And just to save a little bit of time here, I'm not going to bother graphing that function just so we can look at one more example here. Right? But if I were to graph this function on Desmos or my TI, I'm going to see vertical asymptotes at both of those locations on the graph. So then the last example we look at, I'm going to actually alter the third example ever so slightly. So I'm going to take this last example and I'm going to change the numerator to be x plus 1. And the reason I'm going to do that is to show something really interesting here. So if I do that, right, notice that negative 4 and negative 1 are not in the domain of my function. But I want to point out to you here real quick that we now actually get rid of one of the vertical asymptotes. This is really interesting. All right, so you know what, actually I lied a little bit. Let me graph this third example. So I'm going to graph x minus 1 over x plus 4 times x plus 1. So if I graph that, x minus 1 over x plus 4 times x plus 1, here's that graph. Here's the vertical asymptote of x equals negative 1. Right? There's my vertical asymptote of x equals negative 1, and my vertical asymptote of x equals negative 4. I can see that vertical asymptote there and that vertical asymptote. Now, let me go back to my slide real quick, right? What if I change this to x plus 1? Right, this is pretty cool. So I'm going to change this to x plus 1. And look at what happens. The vertical asymptote at negative 1 went away. It's gone. And I only have the vertical asymptote at x equals negative 4. Right? Now, why does that happen? Right, so this is similar to that example we looked at a couple minutes ago when we talked about domain. Right? Think about what's going to happen here. The factors are going to actually cancel out. This is going to simplify. And this function is going to simplify down to 1 over x plus 4. Now remember when we talked about domain. X equals negative 1 is still not in the domain of this function. Right? Negative 1 is still not in the domain. But if I look at asymptotes, here's what the graph really looks like. The graph really looks like 1 over x plus 4. So negative 4 still causes division by 0, but negative 1 isn't anymore in terms of an asymptote. Right? So here's the asymptote negative 4, but let me show you that if I come over here to negative 1, let me get rid of that point. If I come over here to negative 1, I'm going to see what we saw earlier, and at negative 1, I'm going to get an undefined value, and it's going to be a hole in the graph. See, check it out. So there's a hole in the graph. Stay there. There we go. All right, there's the hole. So if the division by 0 in the denominator cancels out, it's still not in the domain, but it's creating what we call a hole in the graph, like we saw in that prior example. If the division by 0 doesn't cancel out, then it's going to create that vertical asymptote. So this example illustrates that for me. So x equals negative 4 is the vertical asymptote, but we have a hole in the graph at x equals negative 1. So back on that prior slide, right here where we defined vertical asymptotes, notice what it says is that as long as the function's in lowest terms, then we will locate vertical asymptotes. Right? So if we go back to that example, right, this rational function's not in lowest terms. So in order to locate the vertical asymptote, we simplify this expression, we put it into lowest terms, and then we locate that vertical asymptote. The other division by 0 turns out to be a hole in the graph. So in general, right, it's a quick summary. To locate vertical asymptotes, we're going to look for division by zero. We just want to be careful that we simplify the rational expression first. The other point that cancels out of the denominator is an actual hole in the graph. All right, one other cool idea about vertical asymptotes is the idea of multiplicity. So if you think back to 5.1 when we talked about polynomials, we talked about if a factor had an odd exponent, like a 1 or a 3, that meant the graph would cross through that x-intercept. And then in a polynomial, right, if the multiplicity was even, the graph bounced off. Well, take a look at what happens with division by zeros. This is pretty cool. So here's an odd exponent, right? So the vertical asymptote has, let's say, an odd multiplicity. Notice how the graph bends in different directions. So it shoots off to plus infinity when I approach from the right, and it shoots off to minus infinity when I approach from the left. However, if I change the multiplicity to be even, notice the graph goes off to plus infinity from both directions. Right? When I change back to an odd, it shoots in different directions. And when I change back to an even multiplicity, it shoots off in the same direction. So just kind of really interesting to note that when the factor in the denominator has an even multiplicity, the graph is going to kind of hug the asymptote in the same direction. And if it has an odd multiplicity, then it's going to go in different directions as it hugs that asymptote. All right, now let's talk about horizontal asymptotes. So back in the beginning of the video, we looked at that graph that had horizontal and vertical asymptotes. And in fact, here was that example. We looked at y equals 1 over x. We saw that there was vertical asymptotes at division by zero. We saw there was horizontal asymptotes at the end. Now, not all rational functions have horizontal asymptotes, but many of them do. And how would we locate those? All right, so basically here's what we're going to do. I have a couple different rules that we're going to utilize. And what the rules boil down to are the leading terms in the numerator and denominator. Now remember, the numerator is a polynomial all on its own. The denominator is a polynomial all on its own. So what we're going to do is we're going to look at the degree of the numerator. We're going to look at the degree of the denominator. We're going to compare those to each other. That's going to determine what our horizontal asymptote is. So let's look at each of those cases. So let's suppose the degree of the numerator is smaller than the degree of the denominator. What that's going to do is give us a horizontal asymptote of y equals 0. So a quick example, here's the degree of the numerator is 1, the degree of the denominator is 2. So we fall into this case. So this graph is going to have a horizontal asymptote of y equals 0. So just to save some time, I'm not going to bother to graph this here, but I would encourage you strongly, plug this in your calculator or use Desmos to graph this function, and you'll see the horizontal asymptote of y equals 0. Now, the second case would be if the degrees are the same. So if the degrees are the same, and if this degree and this degree are the same, what we're going to basically do is take the coefficients. And that's going to be the horizontal asymptote. So a quick example of that would be, here's a degree of 2 in the numerator, degree of 2 in the denominator. So 3 over 2 is going to be my horizontal asymptote. Now let me graph this one for you real quick. All right, so here's the rational function. And notice that there's a horizontal asymptote right here. Remember, we're only focusing on horizontal asymptote. So let's just look at this for a second. And we said that y equals 3 over 2 was that horizontal asymptote. So let me graph y equals 3 divided by 2. And we can see there's that horizontal asymptote of the function, right? That's pretty cool. And notice it's both ends of the graph, right? As I go out to the right, the function in red approaches that horizontal line, right? And as I go out to the left, the function comes down from above and approaches that horizontal line. So I just want to point out to you, as we move out in this direction, the graph's never going to actually touch the horizontal asymptote. It gets infinitely closer to it. And as we move in this direction, the graph is going to get infinitely close and never touch as well. Now remember, vertical asymptotes, we can never touch the vertical asymptote because that creates division by 0. However, what's really interesting here is this horizontal asymptote, the graph crosses the horizontal asymptote. And that's actually totally legit. That's totally legal. Because a horizontal asymptote isn't a division by 0. All a horizontal asymptote is telling me what the graph's look like at the end. So remember polynomials, we had end behavior. Well, this basically is the same thing for irrational. The horizontal asymptote is just the end behavior of the graph. So out at the ends of the graph, I'm never going to cross the horizontal asymptote. I'm just going to get really, really close. Right? Out here at the other end of the graph, I'm just going to get really, really, really close. I'm never going to touch. But when x is quote unquote small, it's totally okay to cross the horizontal asymptote. That's not an illegal step there. All right, so back at our PowerPoint slides, right, there's a couple different cases. We're comparing the degree of the numerator to the degree of the denominator. We said if the degree of the numerator was smaller than the denominators, we're going to get y equals 0. We said if the degrees were the same, we're going to get the coefficient, the ratio of the coefficient. So the only other case is if the degree of the numerator is greater than the degree of the denominator. Now, in this textbook, they break that down into two kind of sub cases. So if the numerator's degree is greater only by 1 unit, then there's what we call an oblique asymptote. And the textbook covers that, but we're not covering that in this class. In fact, you don't have any homework problems in my math lab that cover this case. But for those of you that look in the book, maybe read the book, I just wanted to point that out to you, that if the degree of the numerator is bigger than the degree of the denominator by 1 unit, here's an example of what that might look like, right? This is a degree of 3, this is a degree of 2, right? The numerator's degree is 1 bigger than the denominator's degree. This would give us an oblique asymptote. Now, we're not going to cover this in the class. Let me graph this for you real quick to show you what that would look like, but even though we're not going to cover it, I just want to show you visually what that looks like. All right, so I graphed that equation, and I just want to point out to you that there's no horizontal asymptote for this graph, but there is a what we call an oblique or a slant asymptote. So as I move out to the ends of the graph doesn't look like a horizontal line, it looks like a slanted line. Right? So we can see this oblique asymptote here, and the oblique asymptote goes in this direction. Now, feel free to read about this, all right? If you want to go into the textbook, you want to read about oblique asymptotes, you can, but that's something you'd cover in a pre-calculus course. I'm not going to cover it. It's not necessary for you if you're ending at college algebra, right? But if you're going on into the calculus sequence, feel free to take a look at that, but you will learn about it in pre-calc. Now, the other case, as we kind of mentioned here, we're talking about if the degree of the numerator is greater than the degree of the denominator. So what we're basically going to just say is if the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. So the oblique asymptote might fall into that case, but we're just going to say there's no horizontal asymptote. All right. And, here's an example where the degree of the numerator is greater than the degree of the denominator. We're just going to say no horizontal asymptote there. All right. And we're technically going to lump this example in with this category because we're not covering oblique asymptotes. All right. So quick summary is if we're looking for horizontal asymptotes, we're going to compare the degree of the numerator to the degree of the denominator. If the degree of the numerator is smaller, we're going to say y equals 0 is a horizontal asymptote. The degree of the numerator is same as the denominator, we're going to take the ratio of the coefficients. And if the degree of the numerator is bigger, we're going to say there's no horizontal asymptote. And again, remember the key here, right? Even though we have graphing technology to graph all of this for us, right? As I said in 5.1, we're developing our tools of analysis. So what we want to be able to do is look at the equation of the rational function, and without graphing anything, be able to identify what the vertical asymptotes would be and the horizontal asymptotes would be. So a couple more quick examples here. Let's say we were finding horizontal asymptote. We were given this rational function. What we would do is we compare the degree of the numerator to the degree of the denominator. Since the numerator's degree is smaller, we're going to say that the horizontal asymptote is y equals 0. The next example, we see the degree of the numerator is bigger than the degree of the denominator. So what we're going to say, right, is that there is no horizontal asymptote. Now again, the numerator's degree is 1 larger than the denominator, so technically there's an oblique asymptote here, but we're not covering that. You won't see that on the homework or the test. Another example, here's where the degree of the numerator is equal to the degree of the denominator, so we're going to take the ratio of the two coefficients. We're going to say 8 over 4, or y equals 2 is the horizontal asymptote. Okay, so one last quick example here. Let's put all of this together. So in this section, we are just identifying vertical and horizontal asymptotes. And again, we're doing analysis here. So we're looking at the equation. We're trying to identify the behaviors of this graph. So let's suppose we were asked to find horizontal and vertical of this particular function, x plus 3 over x squared minus 4. So if we're looking for the vertical asymptotes, we're looking for division by 0. Excuse me. Now you want to remember, you want to simplify the function as much as possible first. Because remember that one example, we could have had a hole in the graph if the division in the factor in the denominator canceled out. So I factor the denominator here, and I notice no cancellation occurs. So both 2 and negative 2 are vertical asymptotes. Neither of those are holes. So x equals negative 2 is a vertical asymptote, x equals 2 is a vertical asymptote. So I was thinking of plotting this function, right? Let's say I plot an xy axis. I'm going to have a vertical asymptote at x equals negative 2 and a vertical asymptote at x equals positive 2. So usually when we're graphing, what we do is we put a little dotted line there just to remind us that we can't cross that line. Right? Now remember, that line is not a part of the graph. We're not plotting y values. We're just putting a dotted line there to remind us of the behavior of our function. So then let's say we look for horizontal asymptotes. So for horizontal asymptotes, we're going to compare degree of the numerator to degree of the denominator. So for this example, degrees of the numerator is 1. The degree of the denominator is 2. Since the numerator is smaller than the denominator in degree, we say y equals 0 is the horizontal asymptote. So again, I'll put a dotted line where y equals 0, just to remind myself that's the horizontal asymptote. So that's the main idea in 5.2. Now what we're going to do in 5.3 is we're going to put this together with some other new information, and then we're going to sketch a really nice detailed graph of these rational functions. So in the book, they give you this nice little summary of how to find horizontal and vertical asymptotes. As always, if you have any questions, please post on the discussion board, and I'll see you guys in the next video.